is going to be as x goes to infinity. So basically we have a base infinity to the power 0. Okay, so this is something that this would be considered an indeterminate form. So we need to be able to put it into some form of a ratio so that we can apply L'Hopital's rule. So what we're going to do is we're going to let y equal x to the 1 over x. So whenever we have one of these powers, we want to use the log form. Okay, this allows us then to bring that power down and apply the L'Hopital's to this one. So now we have, I'll write this as a limit as x goes to infinity of log x over x. Okay, so now we have the form that we need to apply L'Hopital's. So that's going to be infinity over infinity. Okay, now we can probably argue that this is a weak over strong and just say it's equal to 0, but let's apply L'Hopital's to it. Okay, so we're going to apply L'Hopital's. Okay, so then we end up with the limit as x goes to infinity of 1 over x over 1. Okay, so we can substitute x infinity in now and we end up with 0. Now we just have to remember that this is not the limit of what we started with, it's the limit of log of y. So that means then that y equals e to the power 0, which is 1. So the limit of this is equal to 1. So again, we should check these by graphing. When we graph these, we can check our solutions for these by graphing. So this one here, we're approaching 0 from the positive side, so log is going to be negative infinity, and we have 0 times negative infinity. Okay, so we end up with 0 times negative infinity like this. Okay, so we need to be able to put this into some ratio form. So it's easier to put the x into the ratio. So I'm going to do this. Limit as x goes to 0 from the positive side. We're going to write as log x over 1 over x. Okay, so then this now gives us the indeterminate form. Okay, it gives us our 0 over 0. In fact, it gives us negative infinity over, and that's 0 from the positive side, which is positive infinity. So we have the condition to apply L'Hopital's. So then we'll go ahead and apply L'Hopital's rule to this. Okay, so then we end up with limit as x goes to 0 from the positive side. We differentiate the log. We differentiate the 1 over x. Okay, so this ends up being the limit as x goes to 0. We just end up with negative x. Okay, plugging that in, we end up with our limit is equal to 0. So that's going to tend towards 0 as it approaches 0 from the positive side. So this is another power one, so we want to be able to put this into the log form of it. So we're going to let y equal e to the x plus x 1 over x. Okay, so when we do 0 to this, we're going to get 1 plus 0. So this ends up being 1, 0 from the positive side, so this is equal to 1 to the power infinity, right? So we need to be able to bring that power out. So use the log form. So we end up with 1 over x, e to the x, plus x. This is going to be log e to the x plus x. Okay, so then we put this into the limit form. Limit as x approaches 0 from the positive side, we're going to end up with log of e to the x plus x. Okay, so this is going to be log 1, which is 0, and we end up with 0 in the denominator. Okay, so that's going to be our condition then. We end up with 0 over 0. We have the condition for L'Hopital's. Okay, so let's apply L'Hopital's. Okay, so L'Hopital's rule, we end up with the limit as x approaches 0 from the positive side. The derivative of that is going to be 1 over e to the x plus x. Chain rule, so we're going to end up with times e to the x plus 1 all over 1. Okay, so plugging in, we're going to end up with, looks like we can evaluate this one here. I'm just going to simplify this before I evaluate it. So we end up with the limit as x approaches 0. We're going to end up with e to the x plus 1 all over e to the x plus x. So this ends up being 1 plus 1 over 1 plus 0. So we end up with the limit of 2. And remember that this is log y equals 2. So then to solve for y, we end up with y equals e squared. And that's going to be our limit. Okay, so I'm going to get rid of that there. And this limit is equal to e to the power 2. Okay, so there's our limit for that one there. Okay, so this one here, we end up with infinity minus infinity. So we're going to have to put this in some sort of ratio to be able to evaluate it. So I'm going to make it into a common denominator. So we end up with square root x minus x all over x square root x. And we'll just write that as a 1 power. That's going to be x to the power 2 over 3. Okay, so I meant 3 over 2. Okay, so that's going to be power 1.5. Okay, plugging in 0, we end up with our condition 0 over 0. Okay, again, I just got to make sure I show that condition. That's very important that you actually show that condition. Okay, on an AP exam, you need to make sure that condition is satisfied and actually show it. Okay, and then I apply L'Hopital's. So this becomes the limit as x goes to 0. This is going to be 1 over 2 root x minus 1 over 3 over 2 x to the power, that's going to be 5, it's going to be power 1/2. Okay, so reduce the power by 1. Okay, so if I plug in 0, I'm going to end up with, divided by 0, so I'm going to get infinity over infinity. Okay, so, or infinity over 0. Oh, okay, I think that one works. Okay, let's just simplify this first, but I think we can evaluate this limit. Okay, so I'm going to multiply top and bottom by square root. Okay, so I'll show that in a different color here. I want to multiply top and bottom here by square root to get rid of that extra root in there. So I'm going to end up with, and let's do 2 like that. Okay, so we're going to get rid of the 2 and the square root, so we're going to end up with 1 minus 2 square root x on top. On the bottom, the 2's cancel out, and x times square root x is just going to give me x. Okay, so in this case here, I'm going to end up with 1 divided by 0, and 1 divided by 0 is infinity because we're approaching 0 from the right-hand side. It's going to be positive infinity, so our limit is infinite. Okay, so there it is. Okay, now make sure that you're aware that this is, although we're dividing by 0, when we divide by 0, we get infinity. So we have to make sure that we evaluate that and not reapply L'Hopital's in this particular case. Okay, so the answer here is positive infinity.